Hi there, this episode is an audio rip of a YouTube video. If there are any references to the screen or to the video itself, then be sure to go over to YouTube and actually check out the video, which will be the same title as this podcast. Thanks. Chapter 44, Protection Against Voltage Disturbances. Now, we're going to talk about voltage disturbances from two common causes. The first cause that we'll discuss will be causes such as man-made events, such as switching induced loads that can create overvoltages, but also faults that can occur on the grid system, such as earth faults on the primary side of the high voltage system, and returning faults coming back into the low voltage system. The other type of overvoltage we'll talk about will be overvoltage of atmospheric origin, such as lightning. So there'll be that as well. And towards the back, we'll also talk about electromagnetic disturbances. It's quite a wordy chapter, this one, and to be honest, for a lot of you, it's kind of beyond scope of what you probably do every day. So a lot of this might seem like you want more information. Unfortunately, we can only cover so much of it because with the regulations, it's just a case of what is here. But if you do want more information on it, or if you want any more specific information with regards to lightning protection, or with regards to transformer distribution, things like that, we can create some content on that. But it doesn't really belong here, unfortunately. So we'll start off with 442, and that is probably one of the longest section titles in this book. So this is the protection of low voltage installations against temporary overvoltages that are due to earth faults in the high voltage system due to faults in the low voltage system. So a fault has occurred in the low voltage system, which has consequently resulted in an earth fault in the high voltage system, which would then require further protection in the low voltage system. Yeah, very wordy. Okay. The following four situations can have an effect on the safety of the low voltage system by creating temporary overvoltages. And let's remind ourselves that these aren't lightning. We're talking about lightning in 443. Yeah, in 443. 442 is more again about faults that can occur in the distribution. So these voltages aren't what we would call like an impulse duration. These are probably a period of time over voltages, but they're not of the same magnitude as such as a lightning strike. So we kind of have to approach them slightly differently. So it could be a fault between the high voltage system and earth within the transformer. It could be a loss of the supply neutral in the LV system. That can happen. I have seen that happen actually a few times. Short circuit between the line conductor and neutral in the LV installation, and accidental earthing of a line conductor that is within a low voltage IT system. Remembering that IT systems have that deliberate high impedance between earth and the rest of the system, and if we short that out, we'll incur high voltages or increasing voltages. Right. General 442.1.1. Section 442 gives the rules for the designer and installer of a substation. So immediately that kind of, for most of you, that's going to be like, oh no. Alright, so we'll have this for completeness, but we won't go into the huge amount of depth with this. It is necessary to have the following information on the high voltage system: the quality of the system's earthing, maximum level of earth fault current, and the resistance of the earthing arrangement. The following regulations consider four situations which generally cause the most severe, and those are given there: fault between high voltage system and earth, loss of the neutral, accidental earthing of the low voltage IT, and short circuit in the low voltage installation. Those are considered as the most common causes of these overvoltages. There's a drawing which I have here, which is on the next page, but before we actually see that, let's just look at these symbols, because these symbols are used in this drawing. So we have section 442, the following symbols are used. IE is part of the earth fault current in the high voltage system that flows through the earthing arrangement of the transformer substation. We have RE, the resistance of the earthing arrangement of the transformer substation. That's there. So there's IE and RE. we have RA, the resistance of the earthing arrangement of the exposed conductive parts of the equipment of the low voltage installation. The low voltage installation, this is the high voltage to low voltage substation. This is the low voltage installation over here. There's RA there. RB is a resistance of the earthing arrangement of the low voltage system neutral for low voltage systems which the earthing arrangements of the transformer substation and the low voltage system neutral are electrically independent. So when we have an independent creation of neutral. UO. In TN and TT systems, normal AC RMS line to earth voltage is UO. So just voltage to earth will be UO. There's no illustration of a voltage measurement between L1 and earth here. So there is no UO on this drawing. No, there's no UO on that drawing. UF. The power frequency fault voltage that appears in a low voltage system between an exposed conductive part and earth for duration of the fault. So this is talking about the stress voltages that occur between exposed conductive parts and earth in the fault, and UF's position is here on the low voltage system. And we're going to see that mentioned in a little bit. We have U1, power frequency stress voltage between the line conductors and exposed conductive parts of the low voltage equipment of the transformer substation during the fault. So here's the substation transformer during the fault. The exposed conductive parts, which are of the equipment, and the voltage between them and the lines. So it's the voltage between that and of the low voltage side to the metal bodywork of the distribution equipment. U2, power frequency stress voltages between the line conductor and the exposed conductive parts of the equipment in the low voltage installation during the fault. So the same principle, but over here in the low voltage system. So it's a stress voltage between exposed conductive parts of the distribution and the lives, and here the same thing, but this part is actually at the substation arrangement. You then have some more symbols for IT specific systems, which we won't go into too much detail now. We then have here 442.2 over voltages in low voltage systems during a high voltage earth fault. So here's the high voltage system, and here's the fault to earth illustrated here. Okay, high voltage to low voltage transformer, substation. This is the thing you have down the road or whatever behind a gate or in a little fenced off area. Fairly local. It's where it'll go from 11 kilovolts to 400 volts or 33 kilovolts down to 400, depends on where you are in distribution's sake. So, in the case of an earth in the high voltage side, the following types of overvoltage may affect the low voltage installation. The power frequency voltage, UF, here, or the power frequency stress voltage is known as U1 and U2. So we need to understand those. Table 44.1 provides the relevant methods of calculation for the different types of overvoltage. So, looking at, familiarise yourself with this drawing. Okay, so substation, high voltage to low voltage, earth fault in the substation on the high voltage side. Yeah, we have here two methods of earth in there. We have stress voltages there, UF for the low voltage side to earth, and in here U1 is from the low voltage side of the substation to the exposed conductive part, and U2 is the low voltage side of the endpoint of the low voltage insulation to the exposed conductive parts. Okay, so trying to take that on, we then have this table. So where high and low voltage earthing systems exist in proximity to each other, two practices are presently used. One is interconnection of all high voltage and low voltage earthing systems, RE and RB. So linkage of these. Separation of high voltage RE from low voltage RB earthing systems. So one solution is interconnecting them, one solution is separating them. Alright. The general method used is interconnection. General method used is common interconnection. The high and low voltage earthing systems shall be interconnected if the low voltage system is totally confined within the area covered by the high voltage earthing system. So again, the high and low voltage earthing systems, high voltage and low voltage earthing systems, whilst it's a common earth, they are representative of their voltages. So this is a high voltage earthing system, and this is a low voltage earthing system. Now, it says they'll be interconnected like this if they are totally confined within the area covered by the high voltage earthing system. So they're within the same chamber, the same containment, the same potential earthing potential area, really, the same earth area. So yeah, it's an idea to have them as a common reference of Earth, because they're in the same housing, aren't they? We then have references to other standards to refer to. Now, Table 4.1, the power, frequency, stress, voltages, and power, frequency, voltage in the low voltage system. With regards to whether the system earthing is TT, TN, or IT, and whether the connection type is RE and RB connected, common, or RE and RB separated, we then have these voltage tolerances for U1, which is this voltage from the exposed conductive parts to the line of the LV system, U2, and UF. And it's just a case of understanding the ways of working that out. So with a TN system, if I had a separated connection, then U1 would be RE times IE plus UO. Alright, so you just need to kind of understand that basically. It's just the principle of understanding the tolerance of the power, frequency, stress, voltage. Now, moving on from that, okay, that's that table there. Yeah, TN, these are separated. We said, that one. Alright, so just familiarise yourself with that table as best you can. Moving on from that, we then come up with some terms such as power, frequency, fault voltage as well. So it says, the fault voltage, UF, as calculated in table 44.1 there, which appears in the low voltage installation between exposed conductive parts and earth, shall not exceed a dangerous level. Note, in a TN system where RE and RB are connected together, their connection to a low voltage global earthing system as described in BSCN 50522- can be considered to be a safety measure against dangerous fault voltages. So there's a suggestion there for them to be connected to a global earthing system. In installations outside a global earthing system, such as IT systems, additional connections shall be made between the PEN conductor and earth. We then have 442.2.2, magnitude and duration of power, frequency, stress, voltage. The magnitude and duration of the power, frequency, stress voltages is a combination of U1 and U2. Were specified in table 44.1, which was this table here. Oh, there. The magnitude of those on the equipment in the low voltage installation due to an earth fault in the high voltage system. So again, earth fault in the high voltage system resulting in a fault in the low voltage system. The magnitude of this shall not exceed the requirements of table 44.2. And this, I do see this one come up a few times. Now, what this table says: permissible power, frequency, stress, voltage. Permissible, allowed, power, frequency, stress, voltage. So, how much voltage is allowed with regards to duration. So, how long is this earth fault in the high voltage system going to last for? If the earth fault is going to last for less than 5 seconds, then we'll allow a potential frequency stress voltage of the nominal voltage between live and earth up to plus 12 volts, 1200 volts. If the fault is actually longer, any time longer than 5 seconds, we restrict it to no more than 250 volts plus UO. So it's just an allowable stress voltage limit. There's requirements for calculation limits. That's just referring to other standards. Other standards 619. To fulfill the above requirements, coordination between the high voltage systems operator and the LV system installer is necessary. Remember that we were talking here about substation manufacturing and substation installation, really, aren't we? Compliance with the above requirements mainly falls into the responsibility of the substation's installer, owner, operator, who needs to also fulfill requirements by BSCN 61936-1. Therefore, the calculation for U1, U2, and UF is normally not necessary for a low voltage system installer, which is what probably most of us are. Okay, but it's here. It's in our book, so we need to be aware of the purpose of its content. Alright, let's move on then to atmospheric origin. So instead of the fault or the high voltage fault problems, let's talk about this kind of problem. So protection against transient overvoltages of atmospheric origin or due to switching. Now in the 18th edition, they've actually rewritten this. They've approached it from a different angle. Instead of having the AQ risk assessment method, we've got a completely different risk assessment method approach now. So, this section deals with the protection of electrical installations against transient overvoltages of atmospheric origin. Transient overvoltages of atmospheric origin. So transients are obviously very, very, very high or very, very, very short duration. Okay, atmospheric origin being such as a lightning stroke. These are transmitted by the supply distribution systems, including direct strikes to the supply system and against switching over voltages generated by equipment in the installation. Right. Let's just get to the interesting stuff. We have overvoltage control 443.4. Now, protection against transient overvoltages shall be provided where the consequence caused by overvoltage could result in serious injury to or loss of human life, result in interruption of public services or damage to cultural heritage, result in interruption of commercial or industrial activity, or affect a large number of co-located individuals. So, again, with regards to the consideration of this, you've got to say, what's the consequence? You know, if it's a risk to human life, then yes, there's got to be consideration. If it's a disruption of business or a risk of something like that, then there's a need to consider it as well. For all other cases, a risk assessment according to 443.5 shall be performed in order to determine if protection against transient overvoltages is in fact required. If it is not performed, the installation shall be provided with protection against transient overvoltages, except for single dwelling units where the total value of the installation equipment therein does not justify such protection. So it's considered that a typical dwelling environment will not have substantial, as it says here, value of the installation and equipment. Okay, so it's considered not to be worth it due to the value of the installation equipment. Now, on the other hand, if you had a large factory or a large commercial installation with lots of valuable equipment, lots of data, lots of money as a consequential issue, there'll be a risk assessment for that. And the conclusion of the assessment for that would be, right, if a lightning strike was to happen and this equipment was to become damaged due to the maybe induced voltages from the impulse and transients, then yeah, maybe there is a need for that. And you'll probably see that in the real world. You'll see schools, you'll see offices, and you'll see lots of buildings with lighting protection systems up on the roof. Okay. Alright, protection against switching of overvoltages shall be considered in the case of equipment light to be producing switching overvoltages or disturbances exceeding the values according to the overvoltage category of the installation, such as generator supplies or inductive or capacitive loads. So we can also create these overvoltages from regular switching of heavily inductive or capacitive loads, large motors and choppers and things like that. 443.5, the risk assessment method. Let's get to that. Calculated risk level, CRL, is used to determine if protection against transient overvoltages of atmospheric origin is required. This is found by the formula CRL is equal to the environmental factor divided by the multiplier of the risk assessment length and the lightning ground flash density. Okay, so we have to be able to find this information. We're going to revisit that formula, but we need to understand this information. So if you turn the page, you'll then have this illustration. So with regards to lightning flash density, we need to identify the location of the installation. So we'll look at this is what we're now using. We'll look at the map and we'll look at the areas. So let's say that we're somewhere, I don't know, East Coast or something, and then we'll pick up, there's Norwich for example, we'll pick that up and we'll look in the book at the same position, and you'll see in this book it's the vertical lines in the regs book, whilst here I've got an orange colour. So we'll go across and we'll see that is, well, this is 0.6, but in the book the vertical lines is 0.8 ng. Okay, and so the value there is lightning flash density FNG, which is flashes per kilometre squared per year. So we'll take that value as a factor. So let's use, we use 0.8 in this case. It's just a geography check, really. So that is the NG. The FENV, the environmental factor, is quite simple. That's just here, the next part. So is it a rural or suburban environment? 85. If it's an urban environment, 850. So that's that bit done. So that's that bit. FANV factor, that's the NG. Now we've got the LP to look for. The LP is a little bit more complicated. So the LP, which stands for Risk Assessment Length, is determined by this kind of formula here. So the LP equals 2 times PAL. PAL is the length in kilometres of the low voltage overhead line, plus LPCL, which is the low voltage underground cable, plus 0.4 LPAH, which is the length of the high voltage overhead line, plus 0.2 PCH, which is the high voltage underground cable. So with regards, it's hard to kind of keep up with all this, but PAL, PCL, they are low voltages, that's the L. Okay, whilst PAH and PCH are high voltages, that's the H. So low voltage, high voltage, high voltage. Now A and C, overhead, underground. So C is underground, A is overhead. Okay, that's how those are broken down. So what we need to do, it says here in the regulations, after it's just gone through that, it says the total length of a PAL plus a PCL and all this is limited to 1 kilometre or by distance from the first overvoltage protective device installed in the power network to the origin of the electrical installation, whichever is the lesser. If the distribution network lengths are totally or partially unknown, because do you know these lengths? Then LPAL will be taken as equal to the remaining distance to reach a total length of 1 kilometre. So whenever, so you find out what you can and then you add the remaining to 1 kilometre. And there's an example there. And then there's an illustration showing you these lengths. So we have underground, low voltage, overground or overhead, low voltage, underground, low voltage, and then underground, high voltage, and overground, high voltage. So it's a case of what, I don't know if you can get this information, then great. If you can get this length, but that's what we need to establish, is the length, because it's a risk, with regards to the longer this is, and then the risk of it being struck by lightning. This is what we're looking for. If this is struck by lightning or this is struck by lightning, then these voltages will come to our system. And that's what we need to watch out for. So it says, just underneath those illustrations, if the CRL is greater than 1000, then protection against transient overvoltages of atmospheric origin is not required. If CRL is less than 1000 volts, so this equipment is quite close, then it is required. So if this is close to us, it's likely to get struck, we're likely to be affected. If it's far away, we're probably farther away. So if it is struck, the energy, the impulse energy, would have been lost or gone elsewhere by the time it reaches our system. So we want this to be far away. That's the idea here. Okay. We then have 443.6, classification of rated impulse voltages, overvoltage categories. Overvoltage categories are defined within electrical installations for the purpose of installation coordination and a related classification of equipment with rated impulse voltages from table 443.2. Rated impulse voltages for equipment selected according to the nominal voltage are provided to distinguish different levels of availability of equipment with regard to continuity of service and an acceptable risk of failure. In English, what this means is when you have equipment, you have to identify a category of voltage tolerance, and you have to ensure that the equipment is installed or established for the category that it's likely to occur. So if we look at table 443.2, you'll see we've got, I mean, this is a restructured way, but if we look at this table, we've got the nominal voltage of the installation, and if we look down at the 230/400 line, which is where most of our systems are, you then have required rated impulse voltage of equipment in kilovolts. And it says over voltage category 4. This is equipment with very high rated impulse voltage, so it's going to tolerate high impulses. For example, energy meter, telecontrol systems. This is going to be your main distribution equipment kind of things. Your main stuff. You then have category 3. This is your distribution boards, your switches, and your socket outlets. So, not as bad as the main, but can, take a lot of the impulse voltage in there with it. We then have over voltage category 2, this one. And this is the actual common one. So this is example domestic appliances and tools. This is your more everyday appliance, and it should be able to tolerate a 2.5 kilovolt impulse voltage. So a lot of your household appliances should be able to tolerate that. And quite often every day you'll have lights flickering and you'll have varying voltages, either again created by harmonics, as we mentioned previously in the chapter 43 video, or due to these overvoltages of man-made or atmospheric origin, where we get these impulses on the grid and we get little fluctuations in voltage. The equipment is supposed to be able to accommodate these these voltages for these transient periods. Alright. If the equipment is very sensitive, though, it may be category 1 and it'll be lower limited of 1.5 kilovolts. So this is why you have a lightning strike or some stuff comes around in the area and some bits of equipment start to not work anymore, whilst other bits of equipment just didn't even notice that there was an issue. It's likely that they are of different categories, and maybe this category has been defeated a little bit. But we do need to make sure that when we select and erect equipment, whether it be main distribution assemblies, sub-distribution assemblies, communications equipment, whatever it is, we need to make sure we identify the position within the premises and within the structure of the network or the wiring systems and the categories within. So closest to the sub-distribution and transformer, if there's likelihood of over voltage switching or lightning strikes or anything, we would need to we'd have like SPDs and stuff in there as well, but we need to consider category 4 equipment, and then category 3 equipment, sub-distribution, and then category 2, and so on and so on. Alright, so we're going to have the equipment protected as it goes within to the installation. Any high transient voltages should go through lots of equipment before it gets to the sensitive stuff. Alright, that's just the way that needs to be. Alright. Towards the end of this section of 443, we do have some examples. Because they've introduced this, they've added some examples. And it'd be worth just kind of revising them a little bit and having a little look-see at them. There's Annex A443. Can use examples on this calculation with regards to the critical lengths. And then there's B443, which talks about SPDs applied to overhead lines as well. So do have a good read of those. Alright. Moving on though to 444. 444 is measures against electromagnetic disturbances. So an electromagnetic disturbance is when we get an electromagnetic field created quite often due to regular switching or changing in the in an AC circuit. So whenever you switch on an AC circuit, it creates electromagnetic field, and then and then it becomes stationary. Changing in current levels is what changes electromagnetic fields, and they can change quite a lot if we have regular switching. And this is very common in a lot of electrical installations to have lots of switching, but quite often we normally would install line conductors with neutral conductors, and so the current will go in one direction and then it will come back in the other direction like that. And so what you'll have is you'll have one electromagnetic field created of equal value in current as the other electromagnetic field going in the opposite direction. So the resultant field created by that conductor is fairly negligible because they're opposing each other, they're cancelling each other out. Now when we have, this is how RCDs work, they indicate an imbalance in the fields due to the fact that one of the conductors is leaking down to earth. So one conductor carries a larger field than the other because one's leaked. Electromagnetic disturbances is the same kind of principle. These electromagnetic fields, if we don't keep the cables paired together, we don't segregate wiring types, we'll have fields created, and if we have large loop areas, we'll end up with issues with transmitting data and with actually transmitting signals through electrical systems. And it's a common problem, and that's what this area looks into. So it talks about them in brief. It then says these are potentially more severe where large metal loops exist. So an example of that, a very, very typical example, here's a consumer unit, and here's a light switch, here's a luminaire, and we chose, let's say we're wiring it in singles and not in twin and earth, we chose to take the single live to the switch, and instead of bringing the switch line back, which would have obviously balanced out the electromagnetic field, we chose to take it away and go to the luminaire the other way. So the neutral went that way, and the switch line went that way, resulting in a big loop. Now that's not constant. The electromagnetic field, when the light goes on, it's there, and it's kind of, that's it. It's not changing. But if you switch it on and off, it has lots of switching operations, then there will be a field, and we can create large loop areas with these kind of scenarios. There are other issues as well, which we'll see later on, with regards to one of the reasons why we don't have PME systems after, on final circuits and things, because we'll have circulating currents. We don't want circulating currents, spinning currents. The other one is where different electrical wiring systems are installed in common net routes. So here's an illustration of a tray with multiple bands of circuits on them. So you'll have power cables, auxiliary, control, and data. So, you have, let's say, here's some power cables, and this power cable has regular starting and stopping. That'll create a field every time it switches. And then this little cable here, maybe with a much lower voltage, maybe 3 volts or 4 volts going to a relay or something, it can induce that voltage. And it can either go and damage the equipment, or it can even operate on that voltage. But we can get induced voltages if we get varying electromagnetic fields due to the fact that they are in this kind of proximity to each other. The solution is to obviously separate them from each other, as illustrated here, or we'll see another solution later on in 525. Okay, so those are common causes. So it describes a little bit here. It says just underneath there, power cables carrying large currents with a high rate of change. This is the key. High rate of change, yeah. di over dt of the interface. Alright. The starting current of lifts currents controlled by rectifiers, for example. These can induce overvoltages in cables and information technology systems, which can influence or damage information technology equipment or similar. Okay, it's varying changes electromagnetic fields. In or near rooms for medical use, electromagnetic disturbances associated with electrical installations can interfere with medical equipment. The requirements and recommendations given in this section can give an influence on the overall design of the building, including its structural aspects. We'll see that with the equipotential bonding networks, where one of the bonding networks recommends having a whole floor laid out as a grid for earthing. So measures to reduce electromagnetic disturbances could result in a building structure being adjusted. And then there's some supplemented requirements, the telecommunication equipment requirements, equipotential bonding and earthing in buildings, IT, and electromagnetic compatibilities. Alright, so common sources we have. Common sources of these electromagnetic disturbances we have switching of devices of inductive loads. Now an inductive load is a load with a large coil within it. And what we have is when we have a coil, we have obviously, you have a large coil, you put power through a coil, it ends up having a back EMF. Yeah, and that's where we actually get things, we'll end up with a back EMF which will oppose current and it creates an impedance. And what we end up with is a lagging effect, and we get a huge current spike due to the switching of inductive loads. Fluorescent lighting also have capacitive loads, such as the capacitors in any fluorescent lighting. The opposite of inductive loads, they obviously charge capacitive plates, which lead, they pull the current ahead. So, the inductive and capacitive components result in reactance, inductive capacitive reactance. Not in this video, but I have done a video similar to that, a ZS testing video where I talked about inductance and capacitance in this area. But I did talk about how they affect electromagnetic fields. Welding machines, rectifiers, choppers, frequency converters, lifts, transformers, switchgear, power distribution buzz bars. The behaviour characteristics of all this equipment results in electromagnetic disturbances being very, very common. Measures to reduce electromagnetic interference 444.1. .4.2. The following measures will be considered where appropriate. We have where screen signal or data cables are used, care could be taken to limit a fault current from power systems flowing through screens. So I have a piece of equipment here and a piece of equipment here, and I have screened equipment. I have cabling that's screened, and obviously the screening is earth. There's an earth path through that, and that obviously protects the sensitive cabling within that. The problem with having this as an earth is if it's got a reference to earth, it can become a pathway for an earth fault. And if it becomes a pathway for an earth fault, it kind of contradicts its purpose, because it's there to screen the cables within it, and we may end up using that screening as a method of carrying much higher current through, which will have a very, very negative effect on those cables. So what it's suggesting is when we do have a screening system like this, consider that if it can be utilized as an earth fault return path, not intentionally, but it can happen, a bypass conductor being put in there to reinforce the screening, which is going to be a much, a copper conductor, maybe like a 4mm or a 6mm, a nice low resistance conductor. So any fault path current, any fault current going in here to earth will go down this way a lot more than it will go this way due to the simple lowest resistance. So a bypass conductor is considered there. We're going to see a bypass conductor used a little bit more in a minute. It also says the use of a surge protected device or the install such as SPD here. It also says the installation of power cables close together in order to minimize cable loops. So this is the scenario we had said earlier on, and it suggests minimizing them like that. Minimize this loop area. And installation of the separation of power signal cables. So own wiring systems. And then the installation of an equipotential bonding network. Now, the installation of an equipotential bonding network is actually covered in the annex from page 116, Annex A444. And without going into it too much, it just introduces common methods of establishing a bonding network depending on the scale. So the first one recommended, A444.1.1, the protective conductor in a star network, which is just like this one here on this floor. This type of network is applicable for the small installations associated with dwellings, small commercial buildings, etc., and from a general point of view, the equipment that is not interconnected by signal cables. So there's no interconnection between any equipment there. They are just bits of equipment bonded through a star method. You then have the multiple mesh bonding star network, which is the one on the next floor up here illustrated. This type of network is applicable to small installations with different small groups of interconnected communicating equipment. So we have little groups of connected equipment that is common. Yeah, they're common to themselves, they're common to each other. It enables local dispersion of currents caused by electromagnetic interference. So you have these little meshes, these little grids. Then you have the common meshed bonding star network, which we can see on this third floor up here. Now this is where we come to the question of a structure change. So it's applicable to installations with high density of communicating equipment corresponding to critical applications. Then it says further down, a meshed equipotential bonding network is enhanced by the existing metallic structure of the building. It is supplemented by conductors forming the square mesh. The mesh size depends on the selected level of protection against lightning, on the immunity level of the equipment, and the frequencies of the data transmission. It then does give you a size to not exceed 2 meters by 2 meters in areas where equipment susceptible to electromagnetic environmental interferences are installed. We then have the top one, which is the bonding ring conductor. And it just illustrates there, an equipotential bonding network in the form of a bonding ring conductor is shown on the top floor of the structure. This illustration is actually on the next page if you are looking for it. It then says, this should preferably be made of copper, bare or uninsulated, and installed in such a manner it remains accessible everywhere. Alright, and then there's illustration for multiple floors. So those are common methods to reduce EMIs. Going back though to 444.6, we have, can I get there? Well, we've actually skipped a bit to get to 446. Before we actually look at 444.6, let's just look at these drawings on page 109, 110 and 111. They may look confusing, but let's just look at them and just try to simplify it more. So figure 44.5, this is avoidance of neutral conductor currents in a bonded structure by using an installation forming part of a TNCS system from the origin of the public supply up to and including the final circuit within a building. So the avoidance of a neutral conductor current in a bonded structure. The point here is we're trying to avoid currents flowing around neutral and earth in a spin. Okay, and that can happen if we're not careful. So obviously it's a TNCS system. So if you look at the bottom, public supply, you've got your earth. Now there's no neutral from the public supply because it's actually on that earth. If you follow that earth into the building, it then separates to a vertical neutral. So the earth goes in and then separates, then you have a PE, protective earth, and a neutral going up, both of them. The link between the two though is only at the bottom. So when you look at the neutral, you'll see there's an arrow that represents current. They just go down to earth, and that's it. Now if we had a link between earth and neutral further up, we'd have current going in between neutral and earth, and it will then start returning up. It will start circulating within the system. And that's what we are deliberately avoiding. That's what this illustration is showing. The next one, same scenario, but a TNS system. So you'll notice at the bottom, we actually have the earth and a neutral separate. There's no link. And as you look further up, there is still no link. So this is just saying to you, don't link neutral and earth. Make sure that the currents go down neutral and they don't return to earth. Otherwise they'll spin around. TT does the same thing. Okay. The TT then goes a bit further by illustrating on the next page, example of substitute or bypass bonding conductor in installation forming part of a TT system. You may have a TT system that comes in and it may feed 3 or 4 buildings on a site. Now you may choose for those 3 or 4 buildings to have their own independent electrode. So your overhead comes into one building, you have an electrode for the earth system of that building, then goes over to the next and you have another electrode for that building. That's absolutely fine because each building is its own potential zone. The issue is, what if we have a common connector between the buildings, such as is illustrated here, signal cabling, something like alarm system or a telephone or something like that, data. So we can have a common connection between the buildings, and that can end up linking the two earthing systems. So what it's suggesting is, if consent, according to the last paragraph, telecommunication cables, etc., cannot be obtained, it is the responsibility of the owner or operator of the cable to avoid any danger due to the exclusion of those cables from the connection of the main potential bonding. The requested solution, if you look at that illustration, you've got the screen signal cables, but then you've got above it a substitute or bypass bonding conductor. So it's recommending that we actually have a bypass conductor, a bit similar to how we had with the screen cable earlier, going to each of these separate TT systems, which kind of links them together. This is where you'd have to kind of think bigger picture about the proximity of the earthing systems. But it's recommending a bypass conductor. You've also got 2 further illustrations on TN systems with multiple sources. So you've got one installation in the middle with a source either side. So you have a source of supply at one point and a source of supply. It could be a standby supply, it could be a separate public supply, whatever. The first illustration is fine. It shows you source 1 is a TN system, and obviously it's a TNCS because with the source 1 side you can see a link between earth and neutral. However, on the source 2 there's no link, and that's fine. That means that there's no looping around. So the currents come in and then they go back. There's no circulating currents. The next illustration, figure 44.10, however, shows you that source 1 and source 2 both link between neutral and earth, and that creates an unsuitable connection because you've got current flowing back in. It's creating a circle within the system, circulating currents. Alright? And we want to avoid that. Okay, so we've got a bit more about buildings, separating buildings within buildings. That's fine. And there's a bit on sizing. Yeah. So 444.5.3, sizing and installation of copper bonding ring network. So that bonding ring network that we looked at here is saying if we were going to do that and it was flat, it needs to be 25 by 3 mil minimum. Round, 8 mil minimum. Alright. Short and sweet, but those can be a question or something. So those are the sizing of the bonding ring network. You have an earthing busbar 444.5.7. Earthing arrangements and equipotential bonding of information technology installations for functional purposes. If an earthing busbar is required for functional purposes, consideration will be given to the extending the main earthing terminal of the building by using one or more busbars. We sometimes change the name of that from main earthing terminal to and there'll be another name for it. Looking at the cross-sectional area of that, for installations connecting the supply having a capacity of 200 amp per phase or more, the cross-sectional area of the earthing busbar should be not less than 50 mils copper and should be selected in accordance with regulation 444.5.2. And for supplies having capacity less than that, then you'll size them with table 54.8, which we'll cover in chapter 54 later on, which is the sizing of the protective conductors. We then have 4446, segregation of circuits, which, you know, is fairly simple. Cables that are used in band 2 voltage, which is low voltage, and cables that are used at voltage of band 1, which is extra low voltage, such as, you know, cell, PELV, etc., which share the same cable management system or the same route, shall be installed according to the requirements of 528.1 and 2, which we'll cover later on, obviously in chapter 52. But it'll talk about segregation of the cables, so compartmentalization. You know, this could represent a dado trunking that you put into an office or a school, where you've got power in one section and data in the other. Okay, so we'll talk about those later on, but we need to consider segregation of the circuits to reduce electromagnetic interferences. And 445, just to round off this section, is protection against under voltage. Suitable precautions will be taken where a reduction in voltage or loss of it could cause danger. Provisions for a circuit supplying a motor will comply with 55213. If current use equipment or any other part of the installation may be damaged by a drop in voltage, it is verified that such damage is unlikely to cause danger. One of the following will be adopted: suitable precautions against damage foreseen, or it should be verified in consultation with the person or body responsible for the operation and maintenance of the installation that the damage foreseen is an acceptable risk. So, you know, you need to consider the need for under voltage protection. Under voltage protection could be signed as detailed as an under voltage device that monitors certain levels of voltage. It could just be your simple motor start stop. A motor start stop, you know, your red and your green start stop button. You know, that it could be as simple as that, where, you know, you've got a 3-phase motor and you lose L2, so the L2 disconnects and it disconnects all three. It's it's all phases or nothing. That is also under voltage protection, because loss of one phase is a loss of voltage. It's an under voltage. Okay. It does say there a suitable time delay may be incorporated in the operation of an under voltage device if the operation of the equipment to which the protection relates allows, without danger, this reduction or loss. So it can delay it if it's not going to damage, if the loss of the voltage isn't going to damage it for the for the duration of the delay. Any delay in the opening or reclosing of a contactor will not impede instantaneous disconnection by a control device or a protected device. So if you have a delay closing, if you have a delay opening or reclosing, it will not shorten the time for instantaneous disconnection. The last bit, where the reclosure of the protected device is likely to cause danger, the reclosure shall not be automatic. So yeah, reclosure meaning, you know, it's turned itself off, the restarting of that, the reclosing of the contact. If that will create danger, then it has to be manually done. That's, you know, that's fairly simple stuff. Okay. That ends protection against over voltage and voltage disturbances. The next bit, chapter 46, is new in the 80th edition. It's just a reintroduction. And to be honest, I'll do a very short video on it instead of adding it to the back of this. I'll do a very short video on it because otherwise people will be like trying to look for it instead of seeing it on the back of this one. So I'll close this video here. I'll do a very short chapter 46 video, which will round off part 4 nicely, and then we'll prepare for part 5, which is the next stage in this, and moving on quite well. All right, guys. See you in the next video. Where's the stop button? See you later.